We'll go ahead and get started. We need to finish up just a little bit on oxidation today. You'll recall that we talked about how you can take a primary alcohol and convert it to the aldehyde using a reagent that we called PCC, which stood for pyridinium chlorochromate. And this is an organic soluble source of an oxidized chromium metal. And we talked about the mechanism of the reaction, how electrons from the oxygen would attack the chromium and chlorine would leave, that would generate an intermediate that looked something like this with a positive charge on the original alcohol, oxygen, and a negative charge on the oxygen from chromium. We talked about how there would be a couple of proton transfer steps that would get you to an intermediate that we called the chromate ester. And I'm drawing it this way because in the next step, we had a base come along and do an elimination reaction. Recall that we said that this part of the molecule is basically a good leaving group, and the oxygen attached to that good leaving group we could say is at the alpha position, and therefore the carbon next door is at the beta position. You have a proton beta to a good leaving group, and so you're set up for an E2 style elimination where a base comes along. I think your text shows you chloride. I don't particularly care what you show. And then that E2 style elimination step gets you to the aldehyde. All right. And I should point out that you can use PCC in organic solvent under anhydrous conditions, which is important for what we're going to talk about next. The question was, how do we go from the primary alcohol all the way up to the carboxylic acid? Remember, the aldehyde was like on the third floor of our oxidation tower, and carboxylic acids are on the fourth floor. And it turns out the presence of water is pretty important for getting to the carboxylic acid. So you can use a chromium reagent. Your text has 2 or 3 ways to do this, though I'm going to only ask you to be responsible for one. Sometimes people call this the Jones oxidation, and it occurs in aqueous solution. The reagent CrO3 is just chromium bonded to oxygen 3 times. The first step involves, again, as with PCC, lone pairs attacking the chromium, only this time we're going to break a chromium-oxygen pi bond. That's going to get us to exactly the same place as we were previously with the oxidation using PCC. So again, you're going to get the chromate ester, which I'm not going to draw because it's exactly the same as before. There are some proton transfer steps. And then you get again to the intermediate where you have a proton beta to a good leaving group. And the elimination can happen. One interesting thing to point out that I wish I had pointed out earlier with the PCC reaction is it's these electrons on the oxygen that are in this bond later on in the chromate ester between the oxygen and the chromium, and they end up leaving with the chromium. So that's where the oxidation happens. 2 electrons are now gone from the molecule. And if you compare the starting material to product, we basically lose 2 electrons and we lose 2 protons. The first one we lose when we do the proton transfer step. The second one we lose here. And this is why sometimes people call oxidation reactions dehydrogenation. We don't do that a lot in organic chemistry, but there are tons of enzymes that are called, that do oxidation reactions that are called dihydrogenases. And that's because a 2-electron oxidation involves losing basically all the components of hydrogen, 2 protons and 2 electrons. All right, but if using the Jones oxidation, we get to the aldehyde, the question is, how are we able to go on further? Questions so far sounding familiar? Okay. And the answer has to do with the fact that you're in aqueous solution, and under those conditions, the aldehyde is in equilibrium with a related molecule called the aldehyde hydrate. You get this by adding water to the aldehyde. The mechanism for that reaction is not that hard, and we could learn it now, though I've decided not to, because you're going to learn it in detail in 352. So sort of just stay tuned for that. It really isn't bad, and you can figure it out using the homo-lumo things we talked about. But the point is that under aqueous conditions, we can get to a molecule that has another hydroxyl group, and then we can do a second round of oxidation. And again, I won't show you all the intermediates, but in the end, you're going to get to an intermediate that looks like this. And again, you're going to do the elimination reaction. Chromium will leave with another set of electrons, and that then gets you to your carboxylic acid. All right. Some questions that came up during the first hour were, does this work for secondary alcohols as well? And the answer is yeah. No problem. You can take a secondary alcohol doing the Jones oxidation. And I guess when I say no problem, I should say yes and no, because you can certainly oxidize to the ketone. And under aqueous conditions, you can even form the ketone hydrate. But at that stage, there is no beta proton to remove. And so you're stuck. You can't do a subsequent oxidation step. Okay, so with secondary alcohols, you can do the PCC oxidation to get the ketone, or you can use the Jones oxidation. Different situations call for different solutions, but you can't get to a carboxylic acid from the ketone using this method. And of course, for the same reason, you wouldn't be able to use this method to oxidize tertiary alcohols either. All right, questions so far? Yeah. Would this reaction go all the way? Is it reversible? It actually depends on the identity of the ketone. If you put a ketone in aqueous solution, different ketones will have different relative percentages of hydrate versus ketone. I would, on a predict products question, the ketone would be just fine as the final product. Others? Is anybody? Okay. So now we want to talk about some reduction reactions. And most of the reduction reactions that are interesting, you're going to learn in 352. In 351, we're going to focus on reduction of alkynes and alkenes. Now, because my penmanship is sometimes bad when I'm in a hurry, and because for whatever reason I don't like saying alkene, I'm going to also use the term olefin. That'll help you tell what in the heck we're talking about. All right, so let's start with an olefin. I'm choosing this cyclohexene, this dimethyl cyclohexene molecule. And recall that we've said that in many cases, reduction in organic chemistry means an increase in the number of carbon-hydrogen bonds. So what if you could add hydrogen across a double bond to get the fully unsaturated molecule. And it turns out that we have a catalyst that will facilitate this process. It's actually thermodynamically favorable to lose the carbon-carbon pi bond and the hydrogen-hydrogen sigma bond, and to gain two new carbon-hydrogen sigma bonds. And both of the hydrogens, when we use this catalyst, get added to the same side of the original double bond. So this is another example of a syn addition. And as I said, this is downhill in energy, but you could put the olefin in with hydrogen, and without a spark or without any catalyst, nothing would happen. But the catalyst facilitates this process. And the catalyst we're going to use is a transition metal called palladium, and its symbol is PD. We're going to use it in its zero oxidation state, so sometimes people will write that PD with a little zero. And we're also going to use it immobilized on carbon, or actually charcoal. And we'll abbreviate all of that. Palladium metal immobilized and mixed in with carbon or charcoal as PD/C, palladium on carbon. All right, and you can buy different compositions of palladium versus carbon. A common composition is a mixture of about 10% palladium and carbon. But how does this react? How does this catalyst facilitate the reaction? The mechanism you're not going to be responsible for. What I will show you is more of a way to remember what happens than an explanation for how it happens. But envision at the microscopic level, these spheres might represent individual palladium atoms. I'm making no comment whatsoever about how close they are to each other, nor am I saying anything about where the carbon is. But basically, palladium takes hydrogen and it breaks the hydrogen-hydrogen bond, and it replaces that with bonds between the metal and hydrogen, a metal hydride. And again, I'm not pushing arrows for this, but it's important to know that the individual hydrogen atoms are held at a surface so that when the olefin approaches, remember the pi bond is planar, and so as the olefin sits down on that surface, the hydrogens will get delivered both to the same surface. And this is why it is a syn addition. If you wanted to push arrows, I suppose you could do something like this, though that's more of a reminder of what happens than an explanation for why it happens. But you use the metal surface to break the hydrogen-hydrogen bond, and then the olefin accepts both hydrogens from the same face. Okay? Questions so far? Your text maybe will call this catalytic hydrogenation. All right. Anything? I chose this example to illustrate the stereochemical issues, that it's a syn addition. Of course, for a lot of other alkenes, it wouldn't be, the stereochemical issue wouldn't be important at all. If you did catalytic hydrogenation of this trans olefin, you wouldn't be able to tell in the final product which side the hydrogens got added to. But this allows you to take an olefin and reduce it to the corresponding alkane. And this will work not only for olefins, but it also works for alkynes. If you use hydrogen and palladium on carbon, you can deliver two equivalents of hydrogen across the two pi bonds of the alkyne to get the alkane. Some of you may, wonder, is it possible to just add one equivalent of hydrogen and stop at the olefin? And the answer is generally not. The olefin, once it forms, can go on immediately to react with any remaining hydrogen. And you run the risk of getting a mixture of products. And so generally we'll add an excess of hydrogen. Plus it's kind of hard to measure out a mole of hydrogen. I haven't told you anything about the practical aspects of doing this reaction. If you join an organic lab and decide to do this, you need to get trained very carefully because hydrogen is flammable, and in the presence of palladium and oxygen, you can actually start a fire. So there's some tricks to how you do this. Go ahead. Uh-huh. Yeah, and let's see. Up above here or for the trans? Yes, the question, I think, for those of you that are at home is, are the hydrogens added to this trans olefin from beneath? They can add from above or below. They would have to be added to the same side. But in the product, there are no stereocenters there, so we actually can't tell what happened. I suppose if we had made these deuteria, heard it both ways, that you could tell in the product, but as it is, you couldn't. Okay, sorry, others? Why does it say, from home, Sierra, why does it say H2 excess on that reaction with the alkyne? I wouldn't require you to show this. I'm just making the point that generally with this method, you cannot stop at the alkene or the olefin. You have to go all the way to the alkane. All right. Other questions? So what if we wanted to stop at the olefin? We've actually got a couple of methods for that. So first, to reduce the alkyne to the cis olefin, we want to take advantage of the syn addition that is given by using the palladium catalyst, but we want to decrease the ability of the palladium catalyst to do the reaction so we can stop at the olefin. Your text describes the strategy of poisoning the catalyst, which means adding some things to the palladium catalyst to reduce its ability to react with the olefin. Your text mentions what some of those things are. It won't be important for our discussion. I think lead is involved and quinoline, a compound called quinoline is involved. But for our purposes, we're going to use something called the Lindlar catalyst. It's a poisoned version of the catalyst. You can think of it as a proprietary catalyst that catalyzes this reaction and allows you to stop at the cis olefin. So if we used an alkyne like this, we used hydrogen again, but instead of using palladium on carbon, we used the Lindlar catalyst. That would get us to the cis olefin, again because it involves this addition happening at a surface and from the same side of the alkyne. All right, so we haven't discussed mechanism there. There's not really a mechanism for you to memorize. You may need to memorize the detail that you get the cis olefin from the alkyne using that method. And you want some practice with that. There's another strategy for getting the trans olefin. And unlike the syn addition with the metal catalyst, this reaction involves a stepwise reduction of the alkyne to get the more stable trans olefin. So this is kind of another interesting reaction that we're not going to talk much about in terms of how to do it practically. But the reagents are sort of weird. You're going to use sodium metal, which is not the friendliest of reagents to use. You kind of have to, you get sodium in a bath of oil so that it doesn't get exposed to oxygen, and then before you use it, you have to actually cut the metal. It's really weird. It cuts with a butter knife or something that's even weaker than that. But you do this reaction with sodium metal in liquid ammonia. Ammonia is a gas, by the way. The stuff you buy at the store is ammonia dissolved in water. You can get ammonia in a gas cylinder, which you can then put into a reaction vessel and condense on a really cold surface, and then it drips down into a flask. It's a colorless liquid, but then you put the sodium metal in, and it starts to dissolve in the liquid and form a sort of dark, deep blue color. And what seems to be going on as that happens is the sodium metal becomes sodium cation plus an electron that gets ejected. Though it's not just the electron hopping around on its own, it actually is probably, reality is definitely more complicated than what I'm representing, but you can think of that electron as sort of hydrogen bonding to individual ammonia atoms. Alternatively, you can, molecules, you can think of that electron actually being delocalized among multiple ammonias. But in any case, that dissolved electron is what gives the solution the blue color. So it's kind of cool if you wanted to know what an electron looks like. Well, it looks blue under these conditions, though you're not actually looking at a single electron, so there's that. In any case, this reaction gives you the trans olefin. And your text does present a mechanism for this reaction, though I'm choosing not to have you learn it, or not to require you to learn it, or to be responsible for it. It's somewhat difficult to rationalize based on the orbital arguments that we've talked about. Basically what happens is one electron gets added to the alkyne, it gets a negative charge and then picks up a proton. You get an intermediate, another electron gets added, it gets a negative charge, you add the proton in a second step. Because there's two different steps, then you're allowed to get the more stable trans conformation. Okay. All right. Questions? I'm sorry, did I miss a hand, Staten? Yeah.
So I might have missed this during the lecture, but do these two always stop at the alkene?
Yeah, we can use these to stop at the alkene.
Okay. Can they proceed on to?
Can they proceed on under some situations? I don't know the answer to that.
Okay.
So as a practical issue, that would be something to be concerned about in a particular case. And
Okay.
what you generally do when you're doing reactions on organic molecules is you look in the literature to see somebody who's done something similar first, and you try to, at least the first time, try to follow their conditions as closely as possible so as to get similar results. So my guess is yes, most of the time you can stop. Yeah. All right, others? So the two different stereochemical outcomes of reducing the alkyne allow us to stitch together these reactions with some other reactions that we've learned recently to solve some challenging synthesis type problems. So as an example, imagine starting with an alkyne and ending up with the following diol. And just for fun, so we don't have to deal with some issues, let's have these R groups be the same thing. In fact, let's have them be methyl groups. I realize that erasing is easier for me than it is for you. And I rejoice in that fact. Sorry, don't rejoice at your misfortune. So, how might we do this? As with any synthesis problem, you can start at the beginning, but sometimes it's also useful to start at the end. So, let's look at the final product. Look at the bonds that are there. We've got two carbon-oxygen sigma bonds. and we no longer have the pi bonds from the starting material. So one question might be, do we know a reaction where this particular diol would be the product? You think anything we've done recently that gives you a product like this? Yeah, go ahead.
Would it be water and H2SO4?
Water and H2SO4, starting with the alkyne, you mean?
Not with the, no.
Okay. So so if you use water and H2SO4, what starting material are you thinking about?
Probably not.
Okay. So if it were an alkene, that's a good way to get one hydroxyl group on an atom, because you can do alkene hydration, and that would put a proton on one of the carbons and an OH on the other. So that gets you one, though it doesn't get you two. Others?
If you can get the epoxide, then you can open it with the, like what he was saying, the OH and H2O.
Oh, okay. So what about epoxide opening? Because we talked about using MCPBA to make an epoxide and then opening it up with like hydroxide and water. Okay, now the question is, what kind of alkene would we need to start with? We've got to get the stereochemistry right. So do you remember what we called this series of reactions? It was a dihydroxylation series, and we said it was, you remember, was it syn or anti? Anti, right. The epoxide one was anti. So that would mean the OHs come in on opposite sides. Sorry?
The Osmium tetroxide.
Okay. So another option that you guys are mentioning is the osmium tetroxide dihydroxylation. And that's the syn dihydroxylation. This is anti. Both can work to give us this product, but the starting materials will need to be different. So what do you think about the starting material for the syn dihydroxylation? What would that need to be? The cis alkene. Okay. Then what about for epoxide? Trans. Yeah, and trans will work just fine. The epoxide we would get from that would look like this, plus it's an enantiomer. And then if you opened it up, the second OH comes in from behind. And it just so happens that if we rotate around carbon-carbon bonds, we can see that we've made the correct compound. So this is one of those fun cases where there are multiple ways to get the desired product as long as you follow the correct stereochemical outcomes. Okay, questions about that step backward? Now, we're not yet to the allowed starting material, so do we know of a reaction? Yeah.
Do you have a key to your office?
Oh, hey, Dal. I didn't know you were there. Dal and Logan. This is my son, Dallin. I can't remember if I told you guys about the fateful day in London with Dal. Maybe some of them. Dal's a good sport. That was surreal. I knew he was coming, and yet I didn't expect him to show up in the classroom. Is that the one I always complain about? Probably. So Dallin is a really sweet boy. When he was little, there was a day he could barely even speak, and he asked for a drink, and I brought him a glass of water, and then he asked for a drink again, and I said, buddy, you have water. But he kept asking for it, and finally he said, Mama. And he wanted Amber to have a glass of water too, and he used to gesture like this to mean everybody, and he wanted everybody to be part of things. So he's got a really sweet heart. But there was a really bad day when we were on a trip to London where he sort of walked off on his own, And there was another really bad day at the end of the trip. We were in Paris, and it was hot, and we were climbing to the top of this hundreds of stairs to get to the Sacré-Cœur Cathedral. And it was so hot that day, and Dallin was complaining the whole time. And by the time we got there, I was just so frustrated, I thought I was going to explode. Amber told me, you know what, Josh, we're going to go inside the church and see it. Why don't you stay outside and cool off a little bit? And I stood there looking out on the Paris landscape, cursing my fate. And then when Amber came out with the kids, she said, now if you want, you can go in and see the cathedral. So I did, and I sat down in the pew and knelt down and prayed to God that I would not kill my son, and that things would be okay. And I came out of the cathedral, and it turns out that while I was in there, Amber had bought me a slushie and a Diet Coke, and this is how I know that prayers are answered. And as you've seen, Dallin lived to fight another day, so that's... Okay, sorry. So I asked before Dallin raised his hand, do we know of a reaction that gives you the olefin, the cis olefin from the alkyne? Turn back a page. Which one is that? That's the Lindlar. Yep, using hydrogen and the Lindlar catalyst. On the other hand, if you wanted the trans olefin, you'd use the sodium liquid ammonia. Sometimes people call this a dissolving metal reduction. In any case, you got two different ways to do it. Now, you can bet on a multiple choice exam. I'm going to give you lots of options, one of which will include mixing and matching these to get the wrong stereochemistry, right? So what if I said Lindlar catalyst plus epoxide opening? That would give you the wrong stereochemistry. And in fact, it'd be useful for you to go after class and try to draw what that product would be. Same thing for dissolving metal reduction and dihydroxylation, the osmium tetroxide dihydroxylation. Okay? All right. Anything else we need to say about that? Now, you've probably heard the term hydrogenation before, or hydrogenated. This reaction where we're reducing the olefin, we said it's a catalytic hydrogenation reaction. But maybe when you were young, you were sitting at a table eating something and reading a food product, a food label, and reading ingredients, and maybe you saw that word in there somewhere. I'm hungry. I didn't quite have lunch today, so I brought some things to eat in my bags here. And one of them is pure vegetable oil. Okay. This is from soybean oil. Okay. What else have we got in here? Olive oil. Want to take a swig of that? I don't know. Some people like to dip bread in that. Peanut oil. All right, so if we were at Chick-fil-A, we could dump this thing in the hopper and make some chicken nuggets and those delicious crinkle French fries. My oldest son works at Chick-fil-A. He works in the back of house. And let me tell you about the peanut oil. It gets on the bottom of his shoes, and then he tracks it in on the carpet, which is delightful. Canola oil. I'm not sure what a canola is. It's from a kind of seed. What else? This is a fun one. Coconut oil. Organic. Ooh. All oils are organic molecules. Come on, right? But this says better body foods on it, which suggests to me that if I take a big slurp out of this, fortunately for all of us, it's sealed. Maybe that will solve all my problems. Notice, actually, these are all liquids, but the coconut oil is this translucent solid. Label says, may contain coconuts. Okay. And then what else? Butter. Right? Everybody loves butter. So these are all examples of fats and oils. And it turns out that a hydrogenation reaction is used to convert soybean oil like this into this lovely vegetable oil derived solid shortening, Crisco. All right? Who wants to take a slog of that? Should we pass that around? Okay, so we want to talk just a little bit about fats and oils and then why on earth you'd want to hydrogenate them. So what I'm going to show you now, I will post in the notes. You'll of course be able to see it in the video. There's no need to frantically try to copy anything down. So fats and oils are triacyl glycerols. They're this molecule here. The 3-carbon bit over here is from the triol glycerol, OH groups on each carbon of a 3-carbon chain. And each of those hydroxyls is tied up in an ester linkage. We've learned about esters in chapter 3, though you won't get a lot more exposure to them until 352. Each of these is attached to a long chain hydrocarbon fatty acid, a carboxylic acid with a long hydrocarbon tail. Generally, these tend to be in the range of 12 to 20 carbons long. Some of them we call saturated, and by saturated we mean no double bonds. Each carbon is fully saturated with either carbon-carbon bonds or carbon-hydrogen bonds. I guess saturated refers to all the carbon-hydrogen bonds. And here's a list of some that are commonly found. Most of the ones derived from biological sources have even numbers of carbons. That has to do with their biosynthesis, which is kind of cool. They have names that are not necessarily important, but all of the saturated fatty acids, now that's just the carboxylic acid portion once it's been released from the glycerol. All of these are solids at room temperature. These are melting points in degrees Celsius, and room temperature is about 25. In fact, you could hold all of these in your hands and they wouldn't melt, right? Not that you would want to, but the unsaturated fatty acids have at least one double bond. If you've got one, it's a monounsaturated fatty acid. So you'll see that on food labels. Some nuts have monounsaturated fatty acids. Poly means more than one double bond, but they are all, from natural sources, they are all cis. And that's actually important, and we'll talk about what happens when one of them is a trans double bond for some reason. Interestingly, and we may have talked about this before in chapter 3, when you introduce a single double bond into a molecule, a fatty acid, its melting point lowers dramatically. So the fully saturated 16-carbon fatty acid palmitic acid has a melting temperature of 63. You put one double bond in there at carbon 9, and it's a cis double bond, and suddenly drops down and it's a liquid at room temperature and even at freezing temperature. As you continue to add double bonds, the melting point drops even further. So a good example of that are these 18 carbon chains. Oleic acid with the one double bond at carbon 9, linoleic acid with 2 double bonds, and linolenic acid with 3 double bonds, and they are all cis, and they are at these various positions. Melting temperature drops substantially with each double bond that you introduce. The reason for that is presumably because the presence of cis double bonds in the hydrocarbon chain prevents them from packing against each other tightly and decreases the strength of the van der Waals forces that hold the molecules close to one another, whereas the fully saturated chains pack against each other quite well. This is part of the structure of linolenic acid. I show it to you just to show you that the double bonds are on carbons 9, 12, and 15, and they are all Z. Incidentally, this is an example of an omega-3 fatty acid. We use the Greek letter omega for the final carbon of a fatty acid. It's, you know how with functional groups, we've said, okay, this is the alpha carbon, this is the beta, and we could go on, but eventually we get tired of going through the Greek alphabet, and so we say, forget it, the last one is omega. And so an omega-3 fatty acid is one in which you have a double bond at the third carbon in from the end. Omega-3 fatty acids are associated with some positive health outcomes, and so various food products have started to advertise when they're present. I guess I should erase the peroxide there. That comes later. I don't know, I'm not a food scientist, so I don't know the extent to which having omega-3 fatty acids is a substantial health benefit versus marketing. I do know that you can go to the grocery store and buy eggs that are enriched in omega-3 fatty acids, presumably because they're feeding the chickens a lot of things that have omega-3 fatty acids in them. Either way, from now on through the rest of your life, when you see omega-3 fatty acid, I want you to say to yourself, and perhaps to the people around you, ah, yes, a double bond, a cis double bond on the third carbon from the end, right? And then people will look at you funny in Macy's, and that will allow you to avoid other uncomfortable discussions. This is how you avoid talking to people, by talking to yourself in organic chemistry terms. Believe me, it works. Okay, so let's go through some of the fatty acids that are present in these liquids versus solids from natural sources, and then we'll talk about hydrogenation. I've listed here, and again, you don't need to copy this down, this will all be available, and the pictures of the various oils are here for the folks at home, and nutritional labels. In this column is the number of carbons in the fatty acid. On top, you've got the saturated fatty acids. Here, you've got unsaturated ones. And then over here, you've got percent composition of the fatty acids in these various oils. So as an example, soybean oil, or our Crisco vegetable oil, is mostly unsaturated fatty acids. In fact, about 55% of the one that has 2 double bonds, some with 3 double bonds, the omega-3 fatty acid, and some with just 1, and only a few 16 and 18 carbon chains that are saturated. And that trend follows for the rest of the liquid oils. Canola oil, in this case, is mostly the monounsaturated fatty acid. So if you want to know the difference between vegetable oil and canola oil, there it is. In terms of physical properties, it doesn't maybe make much of a difference. In terms of nutritional properties, again, I don't know. Is it better to have 55% of the 2 double bonds or 57% of the 1 double bond? Peanut oil is even more of the 1 double bond, the monounsaturated fatty acids, and a lot of nuts are very rich in monounsaturated fatty acids. And olive oil is also rich in the monounsaturated fatty acid. Though now look at these offenders over here, coconut oil and butter. They may taste better, but they are loaded up with the saturated fatty acids, which are associated with negative cardiovascular outcomes. I was really surprised when I looked up the composition of coconut oil, because it has some very short hydrocarbon chains. You know, none of the liquids had hydrocarbon chains in the 8 to 10 region, but the coconut does, although 50% of them are 12 carbons long, and there is still some of the saturated fats there. Butter, of course, from milk, got mostly saturated fatty acids. What I wasn't able to get at the store this morning was a thing I observed in the mission field. I served in South Texas, and the grocery store there was H-E-B. This was great. I could speak Spanish when talking to people, but speak English at the grocery store, which was great. But you could buy lard, animal fat, in a 5-gallon bucket. It was this big yellow bucket with a red lid, and on the side it said manteca, which means lard. And you could use that to create the most delicious tamales. In fact, you can tell a good tamale because at higher temperatures the lard becomes liquid and starts to ooze out, and usually it's acquired this red color at some point. And so the tamales that leave pools of red grease, those are the good ones. Those are the ones you want. In any case, yeah, lard would have more of these saturated fatty acids as well. So we want to talk about a couple of things. First, why would you ever want to turn something like this, the liquid into something like this, the solid. Okay, why do you think?
Well, is plus stores better because of the hydrocarbon change can pack well together.
Okay,
They don't degrade.
stores better. It is a solid. Go ahead. You can spread a solid, yeah. So you could, now, has anybody ever taken a knife and spread some Crisco on some toast? Go home and try that, right? In fact, if you want to try it after class, you can take some home with you. So the solid properties are certainly one thing. Another thing is the fact that these unsaturated fatty acids have a limited shelf life. So some of you may have carried some olive oil in your pocket with you on a mission for anointing the sick. Maybe you were in a tropical climate. Maybe you didn't use it a lot. At the end of the 2 years, you bring it home. And then at some point, somebody in your ward calls and asks for a blessing. So you bust out the old vial of olive oil. You open it up and not a good smell, right? If you haven't tried this, go ahead and try it. What happens is that these positions that are adjacent to the double bonds, the allyl positions, are subject to oxidation reactions in the presence of oxygen. You can actually form peroxides and other derivatives of this that don't smell or taste good anymore. Which brings me to the point of talking about the rancid tostadas of 2016. These are not actually them. These are bought fresh today, but here is a nutritional label from Tostadas, and you can see a lot of vegetable oil, palm olein. That means they've got a lot of oleic acid in them, okay? So we go to my mom and dad's house every couple of weeks for Sunday dinner. And mom plans Sunday dinners like a general plans a battlefield. There are contingency plans. There's always more than enough food. And, oh, are we passing around rancid oil? Is this? That's great. It's bad. Okay. So you're going to want to replace that. All right. Anyway, mom plans the dinner with contingency plans, and we're always asked to bring something, but she always has a backup plan because she doesn't trust a member of our family to actually get things done. So I was supposed to bring tostada shells. I went to the pantry. We had some. I pulled them out. We got to the dinner. People were eating their tostadas, and we started to smell and taste something a little bit like the smell you were just smelling from the olive oil. The tostadas were old and had gone rancid. Justifying my mom's fear that I might not actually be able to pull this one off, right? Can't even nail that task. And so fortunately, though, mom had purchased some fresh tostadas, meaning she had anticipated that I would do such a thing. And her planning paid off, and we were all able to eat okay. So one of the reasons why you would want to hydrogenate, and the process, though I don't know what industrial food hydrogenation looks like, it involves hydrogen and a catalyst. One reason you would do that is to preserve food shelf life. So a lot of products that used to be on the shelves, cookies, crackers, chips, used to have hydrogenated oils in them, and they would last for a long time and they wouldn't go rancid. But the hydrogenation process, if not done completely, can be somewhat reversible, and instead of giving you just the alkane and the cis olefin, can sometimes make some of the trans olefin. And that's where this idea of trans fats come from. Incompletely hydrogenated vegetable oils can have some double bonds in them that are now trans instead of cis, and those are associated with negative cardiovascular outcomes. And in fact, this margarine product, Imperial Margarine, they no longer, if you look at the nutritional label, they no longer are incorporating hydrogenated oils. They have some other way to make the molecule solid, some other strategy. But they're going out of their way to tell you there are 0 grams of trans fat per serving. They want you to know we didn't screw up and partially hydrogenate our oils, and so there's no trans fat here. By the way, 0 grams trans fat doesn't actually mean 0, it just means less than some threshold. It might be 500 milligrams, I'm not sure. So be careful. Next time, we'll talk about a similar issue as to why the Skippy peanut butter is solid, whereas the natural peanut butter has this layer of oil on top that the pros just drink themselves before they use the peanut butter. All right. No. See you next time.